हेलो स्टूडेंट्स, इस लेक्चर में हम लोग कोड जनरेशन के बारे में पढ़ेंगे एंड द कोड जनरेशन फेज इज़ द लास्ट पार्ट ऑफ द कंपाइलर एंड it takes the input from either the intermediate code generation phase or the code optimization phase. I am saying either the intermediate code generation phase or the code optimization phase because in some of the compilers the code optimization phase is the optional one. So in that case it will be taking the input directly from the intermediate code generation phase. Now this is the final activity of the compiler, and it is a process of creating the assembly language statements. It is not responsible for generating the target machine code. In fact, it is responsible for generating the assembly language code. Assembly language code will then be passed to the assembler, and that will convert the assembly language code to the machine code, or that is the target code. The code generation phase has certain properties, or the code generation phase of the compiler, of any compiler, should adhere certain properties. First one is the correctness. The correctness means there is certain meaning of the source code or certain purpose of the source code that has been written. The high language code has been written for a particular purpose, and the code generated by the code generation phase, that is the assembly language code, should also depict the same meaning as that of the source code. So when we are generating the code through the code generation phase, the generated code should depict the same meaning as that of the high language code. High quality is the second property. High quality means it should be error free. Any code that we have generated through the code generation phase, assembly language code that we have generated through the code generation phase, should be error free. There should be no error in that, and if at all there is any error, that should have been resolved till the syntactic phase of the syntax analyzer phase of the compiler, and there should be no ambiguous statement in the target code which is generated. Third property is the efficient use of resources of target machine. So the code generation phase should actually be designing the assembly language code such that it uses the resources of the target machine. Target machine means the machine at which it is going to be executed efficiently, meaning that mostly the requirement of the resources is the CPU and the main memory. So you will not have a control of the CPU, but you can have a control of the main memory. So main memory should be efficiently or effectively utilized. You should not allot the memory, or you should not allocate the unnecessary memory. Last one is the quick code generation. Means the code generation phase should generate the code quickly. It should not delay much, because there's not much time left for the code generation, and in fact, whenever we are writing the code, we actually want the code to be compiled very fast, and then the actual activity should be performed at the runtime as required. Now this is a block diagram of the code generation phase. You can see that at the top we have the intermediate code generation or the code optimization phase. The output of the intermediate code generation phase is the 3 address code, or quadruples, or triples, or the postfix notation, or a syntax tree, or a directed acyclic graph. So the intermediate code generation should be generating any of these 5. Fine. Now after that we have a code generation phase. It takes the input from the symbol table and the error handler also. It takes the it takes use of the symbol table and the error handler while generating the target code, or which is also called the assembly language code. This assembly language code is passed through the assembler, and finally the absolute code or the machine code is generated. Now this machine code can be of two types. One is the absolute machine code, or that another one is the relocatable machine code. So we should take the example to understand this. Absolute machine code means, let's say we have a statement and we have the variables which have to be assigned some values. So during the compilation process, in the phase of the code generation, if we have actually fixed up that this variable will go in this location, this variable will go to this location, it is actually called the absolute machine code. For example, I say that the variable is A and it will go to 1000 address, variable is B and it will go to 1002 location. So this actually is the absolute machine code. The relocatable machine code means, let's say you have a target code and that target code is assigned some memory location when it was running for the first time. When the code runs for the next time, it means it is not that we have designed the code for the one-time execution. We have designed the code for the multiple time execution. Fine. So whenever we are compiling the program next time, or whenever we are executing the code next time, it may go to the free memory available at that time. So the memory is not fixed actually. Okay. So we should write the code such that it can be loaded in any part of the memory which is free currently. Okay. So that is actually the relocatable machine code. So we should write the code, or the assembler should generate the code such that it can be loaded in any part of the main memory wherever there is a free space. Okay. For example, if we have, let's say, 4 lines of the code, and the 4 lines of the code is having the address, let's say 1000, 1001, 1002 and 1003 in the memory. So we will say that this is the absolute code. But if we have designed the code like L is the address of first statement, then L plus 1 is the address of the second statement, L plus 3 is the address of the fourth statement. So depending on the value, depending on where we are going to store the program in the main memory, let's say the first time the address allocated is 5000. So starting from 5000 and then plus 1, plus 2, plus 3. So these will be the memory location of the instruction. At the next execution, let's say the memory assigned to my program is 7000. So 7000, 7000 plus 1, 7000 plus 2 and 7000 plus 3. So these will be the addresses of the instruction of my program next time. So relocatable memory code simply means that we are not dependent on the memory, absolute memory. We have written the code and it can be loaded in any part of the compiler, any part of the main memory. Now there are certain design issues for the code generation phase. So first, the design issue is the input to the code generator. So input to the code generation means in the earlier slide we have seen that either intermediate code generation phase is providing the input to the code generation phase, or the code generation phase is providing the input to the code generation phase. Now the input to the code generation phase should be in the specified format. So the specified formats which are acceptable are the 3 address codes, quadruples, triples, indirect triples, postfix notation, syntax tree, and the directed acyclic graph. Right. Second design issue is the target program. Target program should be in such a format that can easily be converted to machine language code by the assembler. It means the code generation phase is generating some target program or assembly language code. So the target code should be, or target program should be in such a format that can be easily converted to the machine language code by the assembler. Third issue is the memory management. Memory management is actually dealing with the process of assigning the memory to the code that we have written and the data items which have been used in the program. So we have already discussed about the absolute code and the relocatable code. So memory management is dealing with that only. So you can read out these statements which are written on these slides. Both front end and code generator performs the task of mapping the names in the source program to the addresses, obviously. So there are certain names written in the program and that should be allocated some addresses. Names used in 3 address codes refer to entries in the symbol table. So whatever names are written in the 3 address code, they will refer to the entries in the symbol table. For example, if I have written x equals to y plus z, so the names x, y and z, all these 3 should appear in the symbol table. Type in declaration statement determines the amount of storage. For example, if I have declared int x, so x has been defined as int. So if it is a turbo to C++ compiler, in that case X will be allocated 2 bytes of the memory. Fine. So type in declaration statement will determine how much space the given variable will take in the memory. Using symbol table information about memory requirements, code generator determines the addresses in the target code. For example, this is about the relocatable code. If we have written go to J as a 3 address code, so jump instruction can be generated by computing the memory address for level J. So this level J will be assigned some memory address, and if I have written go to J, so it will be referring to some location in main memory, and that will be defined by what is the address of J. Next design issue is the instruction selection. Instruction selection is all about if we are dealing with a particular machine. So for that particular machine, there will be instruction set defined. So in the instruction set, there are some fixed fields. For example, 2 operands, 1 result field, and 1 operator field. So if there are 4 fields, we should be providing all those 4 things in the instruction. Fine. And the other one is selection of instruction depends upon the instruction set of target machine. This is what we have discussed. And there should be uniformity and completeness of instruction set. Any entry in the instruction set should not be left vacant. The third one is that if we are using some statements, then the number of statements should be optimum. Means the number of statements that are going to be converted to the target code or the assembly language code. There should not be there should be a limit to the number of instruction. The redundant instructions should not be written. We have also seen this in the property part also, that the code generation phase will generate the statements which will not be redundant. For example, if I have this statement of kind x equals to y plus z, so this can be written as move y r0, meaning that y is transferred to r0 register, and then add z to r0. It means value z is added to the content of the r0 register, and the answer is also stored in r0 register. And then finally the answer y plus z, which is there in the r0 register, has to be transferred to the memory location x. So move r0 x, the value of r0 has got transferred to the memory location x. So if we have the instruction of type x equals to y plus z, we require 3 statements or 3 assembly language statements. So now on the right hand side you see that we have 2 statements, a equals to b plus c and d equals to a plus e. So the rule says that if we have anything like x equals to y plus z, we have to write 3 statements. So for these 2 statements we will be writing 3 plus 3 6 statements in total. So the 6 statements are moving of content b to r0 register, then adding a content c to the content of r0 register. So b plus c has been performed, and then finally transferring this b plus c value to a. So move r0 a. After this we have d equals to a plus e. So a will be transferred to the r0 register, e will be added to the content of r0 register, and then finally this value a plus e will be transferred back to d. So we have 6 statements. Out of these 6 statements, if you see the statement number 3 and 4, which has been shown as the red color statements, these two are, first you are transferring the value of r0 to a, and then in the next statement itself you are moving the value of a to r0. Fine. So this is a redundant load and store statement, meaning that we have transferred something to a memory location, and immediately in the next instruction we are taking those value from the memory location to the register. So this is actually not required. So we will remove these 2 statements, and then we will remain with only 4 statements. So every black colored instruction on the right hand side are taken, and the red color instructions will be eliminated. So the instruction selection is about selecting the minimum number of instructions such that the code can be efficiently or effectively executed, and it will take less amount of the time CPU for the execution. Obviously, if we have 4 statement for the execution and we have 6 statement for the execution, then the instruction set which has 4 statement will take less time as compared to that of the instruction set having 6 statements. The last thing is about use of the machine idioms. For example, if you have to if you have instruction of type I equals to I plus 1, it should actually be written as increment I rather than writing three lines as given in the form of x equals to y plus z. So rather than that, we should use the machine idioms. So instruction selection is a very important one. We should be selecting the instruction which is the proper one, which utilizes minimum number of the instructions, and that uses the machine idioms also. Final design issue is the register allocation. Register allocation is about selecting the set of variables that will reside in the register at each point in the program. Each point means at each instructions we should be deciding that what are the variables, and all those variables will go to which of the register. Fine. Register assignment means selecting a specific register that a variable reside in. So first thing is about what are the variables. We have to select that which of the variables will go to the registers, and then finally we will be deciding which are the specific register where we will be putting the values of the variable. So if we have 4 register R1, R2, R3, R4, so we have to decide we have some variables, and our variable should either go to R1 or R2 or R3 or R4. Fine. So we will have to decide in which register my variable will go. The third one is number of registers used for computation should be minimum. So obviously, if you are using a program and if it uses the minimum number of registers, so other register will be free for the next instructions, okay, and if you are using the parallel programming, in that case the other register will be free for the other program statements. So for example, we have the instruction set t equals to a plus b, t equals to t multiplied with c, t equals to t by d. So let's see if how many register we actually require for representing this set of the instruction. So here we have transferred the value of a to the R0 register. For performing a plus b, we add the value b to the R0 register. In the next statement, we are multiplying c with the content of R0, which actually has a plus b. So t equals to t multiplied with c is performed. Although we have not stored the value of t multiplied with c at the location t, that we will be doing that in the last. The next statement is about dividing the value d by dividing the value t by d value. So divide d R0, whatever is the content of R0 register, you have to divide that by d, and finally you have to store the answer at the t location. So moving the content of R0 register to t. So here we have used only one register, so we have actually represented our program segment in one register only. Now suppose we have a syntax tree which is given at the left hand side. So in this syntax tree, we have to represent the syntax tree with a minimum number of register. Then just in the second column we are taking in which of the register my variables will go. Fine. So if you see that there are 4 different operations which are performed. So minus, minus, plus and plus. So these are the 4 statements which are performed. If you are going from left to right, then we are taking a minus b first. For this a minus b, let's say the content of a is stored in R1 register, content R0 register, content of b in R1 register, and then performing R0 minus R1 and storing the value in R0 register. Fine. So after a minus b, the value is, or the answer is stored in R0 register, and R1 is free. So R1 can be utilized for other purpose. So the right hand side you can see that we have to perform c plus d before any other operation. So for performing c plus d, the value of c is stored in R1 register, value of d is stored in R2 register, and then adding the value of R1 and R2 and storing that in R1 register. After this, we have to perform E minus whatever is the answer of C plus D. So we are storing the value of E in R2 register, and then operation is performed R2 minus R1, and answer is stored in, let's say, R2. Fine. Now after this, we have to perform R0 equals to R0 plus R2, because A minus B is stored in R0 and E minus C plus D is stored in the R2 register. So we have to perform R2 and R0. We have to perform the addition of these two, and finally the answer is stored in R0 register. So we have taken use of 3 different registers for performing this operation. So assembly language code for the same has been written on the right hand side. You can just relate it with these transfer statement and the addition or the subtraction statements. So for this we have used 3 different registers, which is the minimum one. So these are the design issues. Okay, thank you.